Hi guys, so today we are talking about upper motor versus lower motor neuron lesions. Okay, so before we talk about the lesions, let's first discuss the difference between an upper motor neuron and a lower motor neuron. So if you look at this diagram here, these are your upper motor neurons and these are your lower motor neurons. So the upper motor neuron, there's two types. So, or two pathways or two tracts. So we have the corticospinal tract and the corticobulbar tract. So the corticospinal tract, the name kind of gives it away, like the starting point and where it terminates. So the corticospinal starts from the cortex and ends somewhere in the spinal cord. Okay, starts from the cortex, because cortico, and ends in the spinal cord, spinal tract. The corticobulbar tract starts somewhere from the cortex and ends in the bulbar region in the brainstem. Okay, corticobulbar starts from the cortex and terminates in the bulbar region of the brainstem. So where exactly in the cortex do these upper motor neurons originate? So they originate from the motor areas in the cerebral cortex. Which motor areas? So you know we have different motor cortices in the cerebral cortex. We have our primary motor cortex, we have our premotor cortex, and we have our supplementary motor cortex. So these neurons, they originate in the cerebral cortex in the motor areas specifically. So they can originate from the premotor, the primary motor, or the supplementary motor cortex, and they come down through the corona radiata, then the internal capsule, and then they end up in the brainstem. If that's the corticobulbar, they stop there. Okay, they stop there. If it's the corticospinal, then they go all the way down to the spinal cord, to this anterior gray horn in the spinal cord. Okay, so I hope that's clear. So again, let's go over this. Upper motor neuron, two types. Corticospinal starts from the cortex, in the motor areas in the cortex, so like primary motor cortex, premotor cortex, supplementary motor cortex, goes down via the corona radiata, then the internal capsule, goes to the the midbrain, the pons, the medulla. Actually, in the medulla they decussate, but don't worry about that right now. Goes down to the spinal cord in the anterior gray horn. The corticobulbar tract starts from the motor areas in the cerebral cortex, so primary motor, premotor, or supplementary motor cortex, goes down via the corona radiata, the internal capsule, and then it ends up in the medulla, or the pons, this bulbar region in the brainstem. So that's your upper motor neuron. Your lower motor neuron, I basically think of the lower motor neurons as like the destination for the upper motor neurons. So we have two types as well. For the corticospinal tract, the destination is, I told you, in the spinal cord. So for lower motor neuron, we have the anterior gray horn. Okay, because this is the destination of the corticospinal tract. The destination for the corticobulbar tract is actually cranial nerve nuclei located in that medulla pons region. Okay. So I'll say that again. We have two types of lower motor neurons. They are essentially the destination of the upper motor neurons. So we have lower motor neurons in the anterior gray horn and lower motor neurons that is coming off from the cranial nerve nuclei in the bulbar region. Okay. So what else do I need to say? Okay. So basically, with the corticobulbar tract, I told you it ends up in the bulbar region, and here there's this another cell body. So this is the start of the lower motor neuron. So let me just draw this. So that's a start of a lower motor neuron, okay? And then here in the spinal cord, that's a start of another lower motor neuron, okay? So with the spinal cord, so the corticobulbar tract, again, it goes from the motor areas in the cortex goes down to the anterior gray horn of the spinal cord. That's the end of the upper motor neuron. The lower motor neuron starts from the anterior gray horn in the spinal cord and ends up, it terminates. So the axon terminal is here, because now it's going to innervate the skeletal muscles, okay? With the corticobulbar, it starts from the motor areas in the cortex, ends up in the corticobulbar tract. That's where the upper motor neuron ends, and the lower motor neuron begins from the cranial nerve nuclei that then supplies different cranial nerves. So, which cranial nerves? Okay, so here in this example, it's innervating the oropharyngeal muscles. Okay, so that kind of gives us a clue as to which cranial nerve this is. So which cranial nerves are supplied by the lower motor neuron that comes off after the corticobulbar tract? So the cranial nerve nuclei here, located here in the pons medulla region, are cranial nerves 5. So these are the nucleus of cranial nerves 5, 7, 12, and 9, 10, and 11. So obviously cranial nerve 5 supplies, this is trigeminal nerve, it supplies, these are, by the way, these are just, what do you call it, like motor cranial nerve nuclei. Motor cranial nerve nuclei, okay? So cranial nerve 5 obviously is a trigeminal nerve, so it's responsible, it innervates muscles of mastication, like muscles, like chewing muscles, like your pterygoid, your masseters, those muscles, okay? Cranial nerve 7 is your facial nerve, which obviously innervates muscles for facial expression, you know, to let you smile, raise your eyebrows, puff your cheeks out, things like that. And then it also, the nucleus ambiguous has 3 cranial nerves. So it has cranial nerve 9, 10, and 11. So the glossopharyngeal, the vagus, and the spinal accessory nerve. So the nucleus ambiguous innervates the pharynx, sorry, the larynx, the uvula, the soft palate, and these muscles are essential for speech production and for deglutition, so swallowing, speech production and deglutition, okay? And then the last one is the cranial nerve nuclei of the hypoglossal nerve. So this innervates the tongue, muscles of the tongue to let us articulate the words, and yeah. So these are different nuclei. So the cranial nerve nuclei, that is the lower motor neuron for the corticobulbar tract. So I hope this is clear. So let's give an example here. So damage from like here to about there. So this, like any lesion from there to that point, is an upper motor neuron lesion. And any damage from this point here to this point here is a lower motor neuron lesion. So I hope that's clear. Also, just to give you a bit of terminology here, the corticobulbar tract is quite special. So damage to the corticobulbar tract has a specific name. So an upper motor neuron lesion in the corticobulbar tract is called pseudobulbar palsy. Pseudobulbar palsy. Okay, and any lesion in the cranial nerve nuclei here has got a special name as well. This is called bulbar palsy. So lesions in the corticobulbar tract is known as pseudobulbar palsy, and lesions in the cranial nerve nuclei that it kind of like supplies is called the bulbar palsy. Okay, so now let's talk about the causes of an upper motor neuron lesion. So remember, the upper motor neuron lesions are your corticospinal and your corticobulbar tract. So damage from the point of the motor cortex to the bulbar region of the spine the bulbar region of the brainstem or the anterior gray horn, in that upper motor neuron lesion would count as in that upper motor neuron would count as an upper motor neuron lesion. All right. So causes of an upper motor neuron lesion include stroke. So you can have either hemorrhagic or ischemic stroke. And any conditions that would demyelinate those axons of the upper motor neuron. So conditions that can demyelinate the axons of these upper motor neurons include multiple sclerosis, Friedreich's ataxia, and even B12 deficiency. So these conditions would demyelinate the axons. And last but not the least, we can have ALS. And this is a motor neuron disease, and it's damage to the motor neurons because of like the accumulation of like free radicals. So there's many more causes, but I don't want you to focus on the rare ones. I want you to focus on the more common ones, which are stroke and any demyelination conditions like multiple sclerosis, Friedreich's ataxia, B12 deficiency, and obviously ALS, your motor neuron disease, that happens because of that damages the motor neuron due to the accumulation of free radicals. Okay, so now let's talk about the causes of the lower motor neuron lesions. So let me just draw like this is a lower motor neuron. So this is a skeletal muscle here. So and this is in the anterior gray horn in the spinal. Okay, I'm just gonna draw. So, not very good at drawing, really. Okay, so this is a lower motor neuron. It's in the this is in the anterior gray horn of the spinal cord, and then it extends its axon, and then the axon terminal terminates at this like junction between the skeletal muscle and the neuron. Okay, so basically anything that can damage the lower motor neuron here from the anterior gray horn, its axon, and then the axon terminal can cause a lower motor neuron lesion. So let's first talk about things that can damage, that can create lesion here on the anterior gray horn. So things that can damage the lower motor neuron at this point in the anterior gray horn can be something like viruses. So viruses like polio or like your West Nile virus. Also, we have this genetic condition called spinal muscular atrophy. It's an autosomal recessive condition that can also damage the anterior gray horn. Okay, so spinal muscular atrophy. So it can damage it at this point. And anything that can damage the lower motor neuron at this point, so around the actual axon, can also cause a lower motor neuron lesion. So things like neuropathies, okay, so damage the axons because of certain neuropathies. So it can be hypertensive or diabetic neuropathy, as a complication of hypertension and like long-standing diabetes. Or if you have something called the coda equina syndrome, which is the compression of the coda equina due to a herniated disc. So if you're compressing those nerves, you're kind of damaging their axons. So neuropathy and coda equina syndrome due to the compression of the nerves is going to damage the axons of the lower motor neurons. Okay? And anything that can damage it at this point, the axon terminal, would also create a lower motor neuron lesion. So things like botulism, like toxins. So this can damage the lower motor neuron at this point of the axon terminal. And last but not the least, ALS as well. So ALS can cause upper motor neuron like lesion, but can also cause lower motor neuron lesion. Okay, so let's recap. Things that can damage the lower motor neuron lesion, things that can damage the lower motor neuron lesions. Don't know why I keep saying lesion. Things that can damage the lower motor neuron at the point of the anterior gray horn are viruses or something genetic like spinal muscular atrophy. Anything that can damage the axon of the lower motor neuron include like diabetic and hypertensive like neuropathies, or like damage to the actual nerve because of the compression to the nerves, like quad equina syndrome. Things that can damage it at this point would be your would be botulism, so botulinum toxins. And ALS can also damage the lower motor neuron and cause lower motor neuron lesions. Okay, so let's talk about the difference between upper motor neuron lesions and lower motor neuron lesions in terms of its effect on like muscle mass. Okay, so with upper motor neuron, so I told you upper motor neurons, either the corticospinal or the corticobulbar tract, they start from the cortex, from the motor cortices in our inner cerebral cortex. Okay, so in this cerebral cortex, I have what voluntary control of my muscles. Okay, I have voluntary control, so I can either contract my biceps or extend my limb to relax my biceps. So I can do that. I can tell my muscles what to do. So if there is an upper motor neuron lesion, right? If there is an upper motor neuron lesion, I will lose voluntary control of the muscle. Okay, so the cortex controls voluntary muscle movement, which is where the upper motor neuron originates, from the cortex, right? The motor cortices, which gives me voluntary control of the muscle movement. If there's a lesion in the upper motor neuron, I will lose voluntary control of the muscle. That's how I think about it. So if I take away the voluntary muscle control, if I take away the connection between my cortex to my spinal cord, to my muscles, then I can't voluntarily decide to contract my muscle. I can't voluntarily decide to contract my limbs. I can't voluntarily decide to, do something with my muscles. So have you heard of the phrase, if you don't use it, you lose it? This is exactly what happens in upper motor neuron lesions. Because I lose the ability to voluntarily contract my muscles, I don't use my muscles, so I lose my muscles. And this leads to atrophy. This leads to a specific kind of atrophy, actually. This is called disuse atrophy, because I lose the ability to contract my muscles. I'm not using them. Therefore, it's disuse atrophy. So in terms of muscle mass, in upper motor neuron lesions, we see a decrease in muscle mass. And this is not a very significant decrease in muscle mass as compared to lower motor neuron lesions, but it's still a decrease in muscle mass of about 15 to 20%. Okay? So now moving on to lower motor neuron lesions. So let's just quickly think about what happens at the lower motor neurons. So at the axon terminal, they release acetylcholine, remember? So acetylcholine, what it does, it does two things. So it binds to nicotinic receptors that can lead to muscular contraction. So if we have a lower motor neuron lesion, there's a decrease in ACH release at the axon terminal, and therefore less acetylcholine that's binding to those nicotinic receptors, and therefore less muscle contraction. Okay. Also, the second function of acetylcholine is it binds to receptors that kind of lead to a cascade of signaling downstream, down the cells, that stimulate the transcription of certain transcription factors, leading to the synthesis of proteins. Okay? So, if we have less acetylcholine, we have a decrease in the genetic expression for the synthesis of specific muscle proteins. And you know that there's a balance between protein synthesis and proteolysis. So if we're not synthesizing like muscle proteins and we're constantly degrading them, then proteolysis is gonna overcome protein synthesis. And therefore, the combination of not being able to contract my muscles plus I'm not making muscle proteins would eventually lead to a much greater form or much greater extent of the atrophy. So this is why in lower motor neuron lesions, we see a much more significant decrease in muscle mass, around 70 to 80% decrease in muscle mass as compared to upper motor neuron lesions, which is only 15 to 20%. So with lower motor neuron lesions, significant decrease in muscle mass, and this atrophy, by the way, is called denervation atrophy. Okay, so to summarize, in upper motor neuron lesions, because I damage that voluntary, well, this is, you don't really damage it, but I think about it because in upper motor neuron lesions, it originates from the cortex, and the cortex gives me voluntary control of my muscles. So if there's a damage in that pathway, in the upper motor pathways or tracts, then I cannot voluntarily contract my muscles. So if I don't use it, I lose it. So it's disuse atrophy, and it leads to about 15 to 20% muscular atrophy. With lower motor neurons, because the damage is in the lower motor neuron, which releases acetylcholine at the axon terminal, which does two things. So one, binds to nicotinic receptors, stimulate muscle contraction, and two, binds to specific receptors and stimulate transcription factors, which then eventually leads to protein synthesis. So if I can't contract my muscles and I can't produce muscle proteins, then it's going to lead to a much more significant decrease in muscle mass, around 70 to 80%. And this is called denervation atrophy. Okay, let's move on to fasciculations. So fasciculations are actually only seen in lower motor neuron lesions. Okay, fasciculations are only seen in lower motor neuron lesions. So what the hell are fasciculations? So fasciculations are like involuntary, like pathological muscle contraction. So you know when you have like a muscle twitch, like you know when your eyelid twitches, like if I drink lots of coffee, my eyelids, they just start twitching. Or like when I work out a lot, like my muscles, they just randomly twitch. So that muscle twitching is benign, but fasciculations are kind of like that. They're involuntary muscle contraction, but in this case, they are pathological, okay? Definitely not normal. So fasciculations with lower motor neuron, we normally see this like in the tongue. So they would have like, tongue fasciculations. So why does this happen with lower motor neuron lesions? So remember that in a lower motor neuron, at the axon terminal, they release acetylcholine. And I told you acetylcholine has two functions. First function is it binds to nicotinic receptors that then stimulate muscle contraction. The second one, it binds to specific receptors that then trigger like a signaling cascade that leads to transcription factors and then to protein synthesis, okay? So with fasciculations, the main thing that's affected here is if we decrease, okay, let's think in a physiological setting first. So acetylcholine binds to nicotinic receptors, and then they open up nicotinic receptors in the muscles, this is, okay? And then they open up the channels and they allow sodium ions to come into the cell, right? Making the cell more positive, depolarizing the cell, generating the action potential, and therefore generating a muscular contraction. So if we decrease the acetylcholine that's being released from the axon terminal, then what's going to happen is this is going to lead to the upregulation of acetylcholine receptors. Why? Because the muscle's going to think, oh, maybe there's not enough receptors, that's why I'm not getting stimulated so much. Whereas the real problem is we're not releasing, well, the lower motor neuron is not releasing enough acetylcholine to begin with. So the muscle responds by increasing the amount, so upregulating the number of acetylcholine receptors. So normally these acetylcholine receptors are like chemically, these are chemically or like ligand gated. So they only would respond to a ligand or like a chemical binding to it. So like acetylcholine binding to it. But because there's now so many of them, they become mechanically sensitive. So these receptors become mechanically sensitive that even when you like tap the muscle, that mechanical stimulation is enough to generate an action potential. Okay, so that's why in lower motor neuron lesions we see fasciculations. Okay, let's summarize that. So the decrease in acetylcholine leads to the upregulation of acetylcholine receptors. And these acetylcholine receptors then become mechanically sensitive, meaning that there's going to be more sodium ions flowing in, more action potentials, and more muscle contraction. So before we move on to the next slide, I want to highlight the difference between fasciculations and fibrillations. So I told you fasciculations are involuntary pathological muscle contraction, and fibrillations are basically just fasciculations that are represented or expressed on an EMG. Okay, so that's just basically it. Fibrillations are fasciculations that we can see or we can express, we can detect on an EMG. And again, fasciculations and fibrillations are only present in lower motor neurons, okay? Okay guys, so let's move on to the difference between upper motor neuron lesions and lower motor neuron lesions in terms of muscle tone, muscle strength, and deep tendon reflexes. So let's start with upper motor neuron lesions. So let's go back to this pathway, which we should all be familiar with. This is the corticospinal tract. Why? Because it begins from the cortex, it terminates in the spinal cord, specifically the anterior gray horn of the spinal cord. So let's go through this pathway again. The corticospinal tract starts from any of the motor cortices in the brain. So it can be the primary motor cortex, it can be the premotor cortex, it can be the supplementary motor cortex. And then it goes down, and then it reaches the brainstem. So it goes to the midbrain, the pons, and then in the medulla, they decussate. So they cross over to the other side. So they go down to the spinal cord and ends up in the anterior gray horn on the contralateral side. Okay, so this is the corticospinal tract. So as you can see in this diagram, the corticospinal tract can give off some collaterals. Okay, so they can act on these nuclei here. You see this green nuclei. These are your medullary reticulospinal nuclei, because it's in the medulla. Okay, medullary reticulospinal nuclei, which then give off axons to lower motor neurons. So the lower motor neurons are these ones in black. Okay, so we have the corticospinal tract that gives off its axons and then goes to the contralateral side, and then can stimulate or inhibit the lower motor neuron. Okay, so that's very important. The corticospinal tract, because it starts from the cortex, and in the cortex I can voluntarily decide to contract or relax my muscle. So the corticospinal tract can inhibit or stimulate a lower motor neuron. It's a voluntary decision. Whereas the medullary reticulospinal nuclei only has an inhibitory action on the lower motor neurons. Okay, so the corticospinal tract can inhibit or activate the lower motor neurons, whereas the medullary reticulospinal nuclei only has an inhibitory effect on the lower motor neurons. And if you can see here in this diagram as well, we have two types of lower motor neurons. We have alpha motor neuron and gamma motor neuron. So the alpha motor neuron, they go to the extrafusal fibers, which contract and shorten the muscle for the movement of that body part, that limb, that muscle. Okay, the gamma motor neurons, they go to the intrafusal fibers, which contract the muscle spindle, and this is responsible for the stretch reflex. Okay, so let me say that again. There's two types speaking too much, of lower motor neurons. We have alpha motor neuron and gamma motor neuron. So alpha motor neuron goes to the extrafusal fibers, which when stimulated contracts and shorten the muscle for muscle movement. The gamma motor neuron, they go to the intrafusal fibers, which contract to generate that spin, that like stretch reflex. Okay? Okay, so we got that. So now, what then happens if we have an upper motor neuron lesion? So, sorry, I'm a bit ill today, I think. So what happens then if we have an upper motor neuron lesion? Okay, so let me just take that off. Let's just say it's on that side. If we have a lesion here, let's follow this. So from the motor cortex, the motor signals are not going through and decussating to the other side, not going through the anterior gray horn, and not going through the lower motor neurons, right? If we have a lesion here, this means we lose the stimulation of our medullary reticulospinal nuclei. You see here? The corticospinal tract gives off collaterals that stimulate the medullary reticulospinal nuclei. If there's a lesion here, then this green nuclei, this medullary reticulospinal nuclei, cannot cannot inhibit the lower motor neuron. Remember that the medullary reticulospinal nuclei is only can only inhibit the lower motor neuron. So if they're not being activated, they cannot exert their inhibitory effect on the lower motor neuron. And this means that we actually increase the stimulation of these lower motor neurons, because we're not inhibiting them, we're increasing them. Okay, sorry, I drew that on the other side. Okay, so if you have a lesion here, again, we're not stimulating the medullary reticulospinal nuclei, which means we're not inhibiting the lower motor neuron, which means that we're actually increasing the stimulation of this lower motor neuron. And increasing the stimulation of these two types of lower motor neurons, the alpha and gamma. So if we increase stimulation of the alpha motor neuron, we're going to increase the stimulation of our extrafusal fibers, which means that we're going to increase muscle tone. Okay? So that's why we get hypertonia. Also, if we're not inhibiting the lower motor neuron, we're increasing the activation of the gamma motor neuron, which increases the stimulation of the muscle spindles and increases that reflex pathway. So this is gonna lead to hyperreflexia. So that's why in upper motor neuron we get hypertonia and hyperreflexia. It's because of the decrease in inhibition of the lower motor neuron, meaning we increase their stimulation of the alpha motor neuron, leading to increase in muscle tone and increasing the activation or stimulation of the gamma motor neuron, which increases the stimulation of the muscle spindles, increasing that reflex pathway, leading to hyperreflexia. So we've covered tone and the deep tendon reflex for upper motor neuron. How about its effect on strength? So the strength increase or decrease when we have an upper motor neuron. In fact, the strength decreases for both of them actually. For upper motor and lower motor neuron, we see a decrease in strength. But it's two different types. So in an upper motor neuron lesion, it's called spastic paralysis. So the paralysis bit is like your clue for, decrease in muscle strength. Yeah? Spastic paralysis is because of the increase in tone and deep tendon reflexes. Okay? So spastic paralysis, I'll explain this in the next slide because I need to compare this with rigid paralysis. But just for now, I want you to remember that in upper motor neuron lesions, it creates hypertonia, hyperreflexia, and decrease in muscle strength, which is paralysis, but the spastic type, so spastic paralysis. Okay, so let's move on to lower motor neuron lesions. Okay, so if we have damage, the lower motor neuron lesions, I told you there's for lower motor neurons we have the alpha motor neuron and the gamma motor neuron. So if we have a lesion here, Can you see that? If we have, not purple, I'm not using purple. I'm gonna use, let's use blue. If we have a lesion, can you see this? If we have a lesion here, right? So a lesion affecting the alpha motor neuron and the gamma motor neuron, the decrease in stimulation of alpha motor neuron means that there's a decrease in the stimulation of the extrafusal fibers, leading to hypotonia or decrease in muscle tone. If we decrease the stimulation of the gamma motor neurons, we decrease the sensitivity of the muscle spindles and we decrease the stretch reflex activity, which leads to hyporeflexia. And like I said, we see weakness in both scenarios, in upper motor neuron and lower motor neuron lesion. But in lower motor neuron lesion, it's termed as flaccid paralysis. Okay? It's flaccid paralysis due to the fact that we have hypotonia and hyporeflexia. Flaccid just means like because of the decrease in tone and decrease in deep tendon reflex, it's just really like floppy kind of paralysis. Okay, so that's the main difference, and I will talk about spastic paralysis in the next one. Okay, I added this slide here because I think it's very important to know the difference between rigidity and spasticity. So spasticity, like for instance, we talked about spastic paralysis in upper motor neuron lesions, right? We need to kind of differentiate spasticity from rigidity. So spasticity is velocity dependent. So if you the resistance is going to increase with velocity, whereas rigidity, it's velocity independent. Okay, so the resistance stays throughout, doesn't matter if you increase the velocity. Okay, and in spasticity, the resistance is only like in one direction, whereas in rigidity, the resistance is in both directions. So let me explain. Spasticity, like for instance, it's only like when you're extending the limb, that's only when the resistance is felt. But in rigidity, you can feel the resistance both on the extension of the limb and the flexion of the limb. So I hope that makes sense. In spasticity, typically there are no tremors present. But in rigidity, because rigidity is usually seen in patients with Parkinson's disease, there would be tremors, more commonly than not. In rigidity, there's no weakness. In spasticity, there is weakness in the muscle. Also, when we assess the resistance to movement, when we assess the tone for spasticity, we can appreciate this clasp knife phenomenon, which is when there's an initial resistance followed by a rapid decrease in resistance. So let me explain. So for instance, I'm trying to extend someone's limb. So if they have spasticity, there would be initial resistance. It's going to be so hard to extend the elbow. But then I'm trying, and then eventually it just gives out. So there's that initial resistance followed by the rapid decrease in resistance. So resistance, and then it just gives out. That is clasp knife phenomenon. Okay? Whereas in rigidity, we have either like a lead pipe rigidity or cogwheel rigidity. So lead pipe rigidity means that it's rigid throughout the whole movement. So it's rigid the whole way through flexion, or because it's both ways, rigid as well when I'm trying to, rigid during the whole way through in extension and rigid the whole way through to flexion. There's no giving, there's no decrease in resistance. Also, we can see the cogwheel rigidity, which means that there's rigidity the whole way through, but then you also see tremors. So rigid, and then tremors, rigid, tremors, rigid, tremors. And then when you're trying to, flex the limb, rigid, tremors, rigid, tremors. It's like a start and stop, but when it stops, it has tremors. So that's the difference between rigidity and spasticity. Okay, now let's move on to the special tests or maneuvers. So these ones, they're really only positive in upper motor neuron lesions. Okay, these are not seen in lower motor neuron lesions. Okay, let me say that again. These special tests are only going to be positive for upper motor neuron lesions, and you'd not really see them in lower motor neuron lesions. There's three here that I've listed. So the Babinski sign. So the Babinski test basically involves using like the other end of your reflex hammer and kind of stroking the sole of the foot from the bottom, running it like laterally and then medially. And basically, I don't know if you're familiar with the Babinski reflex. So let's actually start with that. The Babinski reflex, basically, when you do this maneuver, this stimulates sensory receptors, which then take the information to the spinal cord and act on like motor neurons and activate muscles around the foot. Which muscles? So the muscles for plantar flexion. So the plantar flexor. So when you do this maneuver, this basically should activate the plantar flexors, right? The plantar flexors, what do? They point the toes down. The way I think about this, they like plant your toes to the ground. So plantar flexion is when it's the foot plantar flexion, yeah? When you plant the toes down. So when you do this, the toes should point down. And why does that happen? Well, that happens, this is the link by the way, why that happens is because upper motor neurons inhibit the dorsiflexors. So the dorsiflexors are responsible for pointing the toes up to the roof or to the ceiling, yeah? If you have a lesion in the upper motor neuron, this means that you lose the inhibition of the dorsiflexors. So when you lose the ability to inhibit the dorsiflexors, this stimulation, yes, would increase the action, would stimulate the dorsiflexors and kind of overcome the activity of plantar flexors. So I hope that made sense. So the Babinski reflex essentially is this is in a physiological setting, nothing's wrong with the patient. When you do this maneuver, you stroke the foot from the lateral side to the medial side as you're going up. What should happen is that the upper motor neuron lesion should inhibit the dorsiflexors and allow the plantar flexors to fire, so allowing the toes to point down. But if we have an upper motor neuron lesion, we don't inhibit the dorsiflexors, so they would just point up and they would overcome the activity of the plantar flexors. That's essentially what I'm trying to say here. So if you see the positive Babinski sign, then this means that we have an upper motor neuron lesion, because this shouldn't happen. So I did pediatrics, and I know that this is seen in babies as well. Babies typically less than 1 year of age. So this is normal in babies. Actually, we expect this in infants less than 1 year of age. It's not pathological in this group of patients. Why? Because their upper motor neuron is not yet heavily myelinated, right? It's not yet heavily myelinated. Therefore, there's a decreased function of this upper motor neuron in babies. So this means that they can't inhibit their dorsiflexors as well as adults can. So their toes would point up and fan out. So Babinski sign is normal in babies but pathological in adults, okay? The next one, the pronator drift. So the pronator drift involves basically asking the patient to extend their arms forward in supination. So supination, remember, supination is like holding a soup. So palms pointing up, extend their arms in supination, and then what the physician is going to do is ask the patient to close their eyes and just tap on the arm. And basically in an upper motor neuron lesion, the pronators, so the muscles that want to do this instead of this, so the muscles that want to pronate the forearms are basically going to be more powerful than the supinators. Okay, so what would happen if there's an upper motor neuron lesion is that the arm would start to drift downwards. So for instance, I have a lesion here. So the arm would start to point downwards and start to like pronate at the same time. Yeah, so this is my starting position, but it should be fully extended like that. And then the physician's gonna tap on my arms, and then the one with the one with the lesion is gonna start moving down and start to pronate. So that's the pronator drift. It's like this, okay? The last one is the Hoffman sign. So the Hoffman sign involves like flicking the nail of the middle finger and watching for that index finger and the thumb to approximate or to come together. Yeah, so flicking the middle finger and then watching for the thumb and the what do you call it, index finger to come together to approximate. Okay, so these special tests are only present in upper motor neuron lesions. Okay, so let's summarize the key differences between upper motor neuron lesions and lower motor neuron lesions. Starting with muscle mass. So we know that there's going to be a decrease in muscle mass for both of them, but in upper motor neuron lesion is going to be like less significant. And the atrophy that we're going to see in upper motor neuron lesion is called disuse atrophy. Okay, so there's minimal decrease in muscle mass, around 15 to 20%. It's disuse atrophy because I lose that voluntary control or ability to contract my muscles. So I'm not using it, so I lose it. So disuse atrophy. Okay. In lower motor neuron lesions, there's a more significant atrophy. So about 70 to 80% of loss of muscle mass. And this is called denervation atrophy. So the problem here is with the acetylcholine. So less acetylcholine is being released at the like axon terminal because there's a lesion in the lower motor neuron. Therefore, we're not gonna stimulate nicotinic receptors so much to contract the muscle, and also we're not gonna stimulate, you know, the release or the production of transcription factors that would then lead to protein synthesis. So we're not synthesizing muscle and we're not contracting our muscle. So that combination is going to lead to a more significant decrease in muscle mass, denervation atrophy 70 to 80%. In terms of strength, like muscular strength, again, for both of them, we're going to see weakness or paralysis, but we're seeing two different types of paralysis. For upper motor neuron lesions, it's spastic paralysis. For lower motor neuron lesions, it's flaccid paralysis. And the way I think about this is related to the tone. Okay, so flaccid means floppy. So with lower motor neuron lesions, it reminds me that it's the floppy type of paralysis. It's flaccid paralysis. Whereas obviously, if that's flaccid paralysis, the other one's going to have to be spastic paralysis. Okay, so moving on to the tone. So in upper motor neurons, we see hypertonia. And hypertonia because of the decrease inhibition of the lower motor neuron, which means increase in the stimulation of the alpha motor neuron, leading to hypertonia. In lower motor neuron, we see hypotonia because we decrease the stimulation of the alpha motor neuron. For deep tendon reflexes, in upper motor neuron, we see hyperreflexia because we basically increase the stimulation of the gamma motor neurons, which increases or makes that reflex pathway more sensitive. Okay, so it's going to lead to hyperreflexia. For lower motor neuron lesions, it's hyporeflexia because we decrease the stimulation of the gamma motor neuron, which decreases that sensitivity of that muscle spindle stretch reflex pathway. Fasciculations are only present in lower motor neurons and absent in upper motor neurons. So they're only present in lower motor neurons because basically the loss or massive decrease in the release of acetylcholine at the axon terminal is going to lead to the upregulation of acetylcholine receptors in the muscles, meaning that they're going to be more sensitive and even sensitive to mechanical stimulation. So that's why we're going to see fasciculations in lower motor neuron lesions, but not in upper motor neuron lesions. Also, we're going to see fibrillations only in lower motor neuron lesions, because fibrillations are literally just fasciculations that are represented or expressed or shown on an EMG. Okay? So the pathological reflexes, so positive Babinski, positive Hoffman, and positive pronator drift, are only seen in upper motor neuron lesions and not seen in lower motor neuron lesions. So how do you remember all of these, you know? So I think about all of these as like a scenario in my head. So for instance, we have like a captain or a general, basically a higher ranking person, and we see like a private, like a lower ranking. I'm not saying she's lower because she's a woman. It can be the other way around. For this scenario, let's say this is the general or the captain, higher ranking personnel in the army, and then a private, which is a lower ranking personnel in the army. So they both got caught and they are both being interrogated. So basically, in terms of strength, because let's say they're both captured, they're both gonna have a decrease in strength. Okay, they're both gonna have a decrease in strength because the captain or general is a lot stronger. Let's assume that he's a lot stronger to begin with. Then therefore the decrease in strength is gonna be less. So it's only going to be 50 to 20% decrease in strength. Whereas the private, because he's probably not so experienced, you know, haven't been really fit for that long, then he's going to have a much bigger decrease in in muscle mass, okay? Or in strength. So 70 to 8% of muscle mass. And in terms of tone, I just remember that the higher ranking one would have increase in tone and the lower ranking one decrease in tone. Same with the deep tendon reflex, higher in the higher ranking personnel and lower in the lower ranking personnel. Fasciculations. So because the lower ranking personnel is probably new to this, you know, and has never been interrogated before, he's so scared that he starts shaking. So, and the captain, because probably this is not the first time he's been captured, he's quite chill. So he doesn't show any fasciculations. He doesn't shake, he doesn't twitch. Whereas the lower ranking personnel start shaking. So we see fasciculations only in the lower motor neuron lesions. Fibrillations, same reasoning. And for pathological reflexes, I think about pathological reflexes as what do you call it? Like torture maneuvers. So, you know, you're kind of stroking the person's foot, you're tapping their arm, and you're flicking their nail. It's kind of like torture maneuvers. So we would only torture the higher ranking personnel because the lower one is probably gonna just die because it's too weak, or probably just gonna surrender. So, you know, we're gonna torture just the higher ranking personnel. So that's how I remember it. You know, it might not help you, but it definitely helps me. So these are basically the summary for the key differences, and this is how I remember it.